Let us discuss regular solids or Platonic solids. Before discussing regular solids, let us look at the 2D version, 2D equivalent of these solids, that is the regular polygons. Regular polygons. How do we define regular polygons? So, regular polygons we can define as a 2D figure, a 2-dimensional polygon. Polygon of course, will be a 2-dimensional. So, polygon with all edges of the same length and all angles equal. So, angles are equal and edge lengths are equal. So, it is equilateral, equilateral and equiangular. Both is required. And of course, you are familiar. So, let us look at examples of regular polygon. You are familiar with equilateral triangle. Triangle. So, it is a regular polygon, all sides are equal, all angles are equal to 60 degree. If you take a square, we have a square, all sides again equal, all angles equal to 90 degree. So, square, this is also an equilateral triangle. But let us look at two examples which are not regular polygons. So, for example, if we consider a rectangle, it is equiangular, but not equilateral. Sides are not equal. Rectangle, equiangular, but not equilateral. So, this is not an example. This is not an example of a regular polygon. Similarly, if we look at a rhombus, so sides are all equal. So, it is equilateral rhombus, equilateral, but not equiangular, and so this is also not an example of a regular polygon. So, equilateral triangle, square. What are the other examples? So, equilateral triangle, square, then equilateral pentagon, regular pentagon, equilateral and equiangular, a regular hexagon, So, equilateral triangle, square, regular pentagon, regular hexagon. Of course, you can have irregular variety of these also. So, the adjective regular is required to classify that we want to have equilateral as well as equiangular, and so on. So on to up to what level? How many regular polygons are there? How many regular polygons are there? The answer of course will be infinity. Infinity. Regular n-gon, you can have a regular n-gon for any n greater than equal to 3. So, with this familiarity, now let us try to generalize this concept into 3D. So, what is the 3D version of regular polygon? The 3D version of regular polygon is a regular polyhedron. Regular polyhedron, also known as Platonic solids, because Plato philosophized about these solids. In his philosophy, they play some role. So, that is where the name Platonic comes, but a regular polyhedron. So, what do we mean by regular polyhedron? How do we define? So, it should be, to generalize the concept of equiangular and equilateral. So, all edges were same and all angles were same. We now want all faces to be congruent regular polygons. All faces to be regular congruent polygons, and we want all vertices, just like we want equiangular. So, that was the geometry of the vertex in 2D, all vertices to be identical or congruent. Edges, of course, all edges will automatically be equal because we have congruent regular polygon. So, this obviously implies equal edges also. So, regular solids will have all faces identical regular polygons, all edges equal and all corners identical. You already know some of these. So, you have a regular tetrahedron, you are familiar from the tetrahedral interstices and all. So, it has 4 vertices, it has 6 edges, and it has 4 equilateral triangular faces, and the naming is always on face. Hedron is face, tetra is 4. So, 4 faced regular solid. So, tetrahedron is a 4-faced regular solid. You are also familiar with cube. We have been discussing many cubic crystals. Three cubic Bravais lattices, simple cubic, face centered cubic and body centered cubic, all based on a cube. So, cube has 8 vertices and has 12 edges, and there are 6 square faces. 6 square faces, you are familiar with this also. And then octahedron, you can draw. Easy way to draw it is draw it as a square based bipyramid. So, have a square, have a pyramid above and have a pyramid below, and adjust the height of the pyramid such that all triangles are equilateral. So, you can see 4 plus 2 6, 6 vertices, again 12 edges, and you have this time 8 triangular faces, 8 equilateral triangles. So, this is cube, this is octahedron. So, we have tetrahedron, cube, octahedron, and while discussing C60 solid, you also met with one more not so common, but is still quite common in physics and chemistry, is an icosahedron. Recall that the C60 molecule structure was related to icosahedron as because the carbon atoms were located at the vertices of a truncated icosahedron. So, we have icosahedron, let me try to draw for you. So, it has triangular faces, again it has equilateral triangular faces, it has vertices where 5 triangles meet, at each vertex 5 equilateral triangles meet. So, you have 12 vertices, you have 30 edges, and you have 20 faces, 20-hedron, icosa is 20. So, it is a 20-faced solid, very interesting solid, and this is known as an icosahedron. In fact, Tipu Sultan had a very beautiful icosahedron, which is now somewhere in British collection. He had an icosahedral box. So, you can Google search Tipu's icosahedron and you will get beautiful images of the golden icosahedral box which Tipu had made. So, we have these 4 examples of solids which are regular. So, the question now again is how many regular solids are there? How many regular solids? 4 examples we have seen. Can we continue? And we have seen examples only made up of triangles and square, the tetrahedron, octahedron and icosahedron. They were made of triangles and cube was made of a square. So, the question is how many of these are there? Ponder about that. This is very interesting mathematical question. How many regular solids? In 2 dimensions, we saw that there are infinitely many. So, are there infinitely many regular solids in 3 dimensions also? Looks like, because we have one more degree of freedom now, one more dimension. So, the number should not reduce, but it turns out that actually the number is finite, and it is finite not in hundreds, not even in 10. There are only 5 regular solids, only 5 regular solids. 4 I have already shown you the example: tetrahedron, cube, octahedron, icosahedron. The 5th one, which I have not shown you as till now, is what is known as a regular dodecahedron. Dodecahedron, do and deca, 2 and 10. So, it is a solid made up of 12 faces, and let me add an adjective, pentagonal dodecahedron. So, its faces are made up of pentagons. So, 12 pentagons, edges are 30 and vertices are 20. So, 20 corners, 12 faces and 30 edges. This is a regular dodecahedron. If you want to become familiar with these, it is nice to make paper models of these solids. So, I leave this as an exercise for you. Exercise. Make paper models. Not very difficult to make. You can Google. I will show you some examples of the solids which I have made. So, actually my daughter has made for me. So, this is the tetrahedron, you can see, made up of paper. This is the cube, this is octahedron sitting on its face, but the way I drew it was a square dipyramid. So, that is something like this. This square based pyramid, you can see the top pyramid and there is a bottom pyramid also. So, square based dipyramid, and icosahedron, which we saw during discussion of C60 molecule also. So, icosahedron, 20 triangular faces, 12 vertices, each vertex 5 pentagons meet. So, this is the geometry of icosahedron, and finally, the pentagonal dodecahedron. So, this is made up of pentagons. At every vertex 3 faces meet, all edges are identical, and it is a beautiful pentagonal dodecahedron. So, if you have time and if you want to make an effort, you can try to make all these pentagonal solids. Details are all available on the web. So, the proof is also quite simple. Let me not go into that. Proof is also quite simple. Five regular polyhedra. Simple geometrical proof. I will not discuss it here. Look this up, and you will also find a very interesting relationship between the vertices, edges and faces, which was first discovered by Euler and is known as Euler's polyhedron formula. Euler's polyhedron formula, that the vertices, number of vertices plus the number of faces minus the number of edges. This is true, this is equal to 2 for all solids. This is true for all polyhedra, regular or irregular. So, for 5 Platonic solids it is obviously true, but for other non-Platonic solids also this will be true. For example, let us look at tetrahedron. Tetrahedron had 4 vertices, it also had 4 faces, so that makes it 8, but remember it only had 6 edges. So, 4 plus 4, 8 minus 6 is equal to 2. You can verify that is true for all the solids which we have given.